Hello, I am Zahra Ibrahimi, a PhD student at the Chair of Processor Design in the Center for Advanced Electronics at TU Dresden, Germany, and I am glad to present you BioCare, which is an energy-efficient CGRA for biosignal processing at the edge. The most important requirements for health monitoring at the edge are energy efficiency and real-time processing. Normally, 70% of energy in wearable nodes is consumed for processing and less than 30% is dissipated in sensing. So, it is highly desirable to improve the energy for computations. In this context, approximate computing has recently shown significant potentials to achieve such goals. In fact, biosignals are permeated with noise and the algorithms for their processing have shown error resiliency. So, with the help of approximate techniques, we can design health monitoring gadgets with a smaller area, less energy, and higher performance for a real-time health monitoring. The first step is to choose a proper hardware platform. Well, processing of biosignals shows high parallelism potential. In addition to that, the platform for processing of such signals should also be adaptable, mainly for two reasons. First, many customizations are required for different patients having different physiologies. Second, the data path flexibility is also needed to support workload variation, for example, after an update in the application itself. Considering these points, CGRAs have shown to be promising platforms by striking an acceptable balance between ASICs and FPGAs. This is not only because of having flexible data paths, but also because they achieve near ASIC resource efficiency. However, CGRs in the literature, either accurate or the approximate ones, all suffer from large area as they collect the separate instances of functional units in their ALUs. Normally, these components are adder, multiplier, and in some cases divider. In fact, dividers appear only in some ALUs because they are very resource hungry, but still unavoidable in biosignal processing. Such a heterogeneous architecture has resulted in routing overheads, which further imposed a performance penalty in such CGRAs. So, in our BioCare CGRA, we address such a resource challenge by designing a lightweight ALU which features hardware plasticity. This means that rather than collecting functional units separately, in our designed ALU, we have integrated them in one small unit which can be configured to each of such functionalities within the same resources. To this end, we use our earlier designed hybrid multiplier divider which is called SIMDIVE. The architectural details are discussed in the paper. In fact, BioCare CGRA supports SIMD execution model not only by connecting multiple ALUs, but also within each one. We have enabled this feature for the first time in the literature. Each of our ALUs can be programmed at runtime to execute two 8-bit or one 16-bit multiplication or division operation. In this way, less logic and routing resources are used for implementation and connecting kernels operation. To manage such precision variability at runtime, we have performed a sensitivity analysis which has shown 2 points. First, ECG and EEG processing kernels are error resilient, and second, this analysis has revealed which operations can tolerate lower precision without noticeably affecting the final accuracy of the application. To efficiently manage the precision at runtime, we also propose an approximation heuristic which starts to lower the precision of less sensitive operations of the kernels until reaching the accuracy threshold of the user. Evaluations of our CGRA, both at architecture level, the figure on the left, and the application level, the figure on the right, show significant improvement in all aspects, including area, energy, and performance. Overall, BioCare has shown very promising results in processing of ECG and EEG kernels. Especially, it has enabled 61% faster detection with 74% less energy when executing heartbeat detection application through Pan-Topkin's algorithm. BioCare CGRA can also be used for other domains of applications. In fact, we intend to explore its efficiency for image processing kernels as a future track. Here are the most important related references, and thanks a lot for your attention.